right, we are on to Chapter 6b, question number 1. And number 1 says, what factors influence the intensity reflection coefficient at an interface between two different media? The intensity reflection coefficient really isn't affected by the media. It's just more a response to what is reflected and what is transmitted. So at any interface, we have 100% of an energy coming to that interface. We have to keep it 100% no matter what's reflected and what's transmitted. So if 50% is reflected, then 50% needs to be transmitted. If 30% is reflected, then 70% needs to be transmitted. It doesn't really have anything to do with the media, just what is actually occurring with the reflection and the transmission and conserving the energy that came to that interface. All right, and we are on to question number 2. Question number 2 says, why is the interaction of sound at an interface with oblique incidence complex and unpredictable? To be super honest, I don't have a really good answer for you. But what I do want to direct you more to think about is just what's occurring with the angles that you're using with your transducer, how that transducer is angled at the anatomy that you're trying to get, and how that's going to affect the image that appears on your screen. If this is our transducer up here and it's emitting sound into the body, straight from the transducer face, then structures that it hits at a normal incidence are going to send back a really strong reflection. Structures that it hits, though, at an oblique incidence is going to send that sound kind of off in another direction, and we're not necessarily going to get much of it back. And so we talk about, like, if we are saying you're imaging a blood vessel, we say put it parallel to the screen, so when your sound gets to it, it hits it at that 90-degree angle or normal incidence, and then we get these really strong vessel walls. Probably see it a lot with the heart too. If you've got valves, or even like the ventricular septum, if you're parallel with that ventricular septum, it's going to be really difficult to see that ventricular septum really well. So oftentimes you have to come at an angle, ideally 90 degrees if we can, to get that nice separation of the ventricles and to see that septum really, really well. So all of this talk about oblique incidence and normal incidence all kind of again informs how we're going to manipulate this transducer in relationship to the anatomy that we're trying to see. And if we know that oblique incidences don't see as well because of these reflections going off in other directions, possibly, then that kind of helps us to decide, well, I need to try this window to see things better, or I need to do XYZ to get a better image. And that's why we spend some time talking about this. So the actual math that goes into like oblique incidences and stuff, I wouldn't worry too much about it. The nice part is we don't even try to get into it. We just tell you it's kind of difficult and then just give you the things that you really need to know about it, knowing that oblique incidence, if reflection occurs, this angle is going to equal this angle. And then if transmission occurs and there are different propagation speeds in media 1 and 2, we're going to have some refraction during that transmission. And that is kind of the basics of it. Number 3 says, I need help with calculating IRC and ITC. For IRC and ITC, remember that they have to equal 100%. That's really all it comes down to. They have to equal 100%. And when we say coefficient, I want you to immediately think it's some sort of percentage that is occurring. And I want you to think that because when we think coefficients, it's a multiplier of what's happening. So the percentage informs us of any other factors that we would be measuring in that situation. So for example, let's say we're measuring power in this wave, and I say the IRC is 50% and the ITC is 50%. I can say then that 50% of the power is going back and 50% of the power is being transmitted. But what if I'm now looking at this situation in the framework of intensity? Same thing. I can say 50% of that intensity is sent back, 50% of the intensity is sent forward. What about amplitude? Same idea, 50%, 50%. So the IRC and the ITC are coefficients, which tell us we are working in percentages and that we can use these percentages to inform what's occurring with the actual unit or factor variable that we are measuring in that situation. And then they always have to equal 100%. So just to do another mathy example here, this will be our interface. And let's say we are coming in again with 100% of the energy. So 100% intensity is coming in. Our IRC is going to equal 30%. And our ITC is going to equal 70% because they have to equal back up to 100%. We cannot lose energy or create energy, which is why we always have to get to that 100%. So if I said IRC was 30%, you should be able to calculate 70% by taking 100 minus 30, and that equals 70. So IRC and ITC. Same idea, if I'd given you the ITC is 70%, you should be able to take 100% minus 70% equals 30% for the IRC. They always have to equal 100. Now, how this then kind of translates into other things, say then I tell you that the intensity coming in was 100 milliwatts per centimeter squared, and the IRC is 30%, right? And then I ask you, what is the transmitted intensity? Well, because these are coefficients, we now know 30% of the 100 milliwatts was reflected back. 70% of the 100 milliwatts has to continue forward. So we would take 70% of 100, which is 70. And so 70 milliwatts per centimeter squared of intensity propagated forward, and 30 milliwatts per centimeter squared of reflection occurred. So the IRC and ITC always equal 100%. These percentages then can be applied to any intensity values that you get. If I change this to 200 milliwatts per centimeter squared, then 70% of 200 is 140. And 30% of 200 is 60. And so that's how we can calculate IRC and ITC and then apply it to do some calculations for intensities. All right, and we are on question number 4. Number 4 says, when looking at Snell's law and the angle of transmission versus angle of incidence, I have a general question. I understand that when the angle of transmission is less than the angle of incidence, sound travels slower in the second medium. Can you explain again why that is? So unfortunately, sound is actually not going to travel slower in the second medium. It's going to travel faster. So let's go over refraction as a general idea and hopefully give you some tips on remembering all of this. So for refraction to occur, we need to have two things that are true. The first thing that has to be true is that we have to have oblique angle of incidence. We cannot come at it at 90 degrees. That would be normal. We have to have an oblique. It has to come from an angle. Anything other than 90 degrees could result in refraction. The second rule of refraction is that the speeds of the media cannot be equal. Speed 1 cannot equal speed 2. If it does, refraction will not occur. So we have to have a difference of speeds for refraction to occur. So those are the two rules. If you get a question that says anything about normal, your answer will not be refraction. If you get anything in a question that says something about the speeds are equal in both media, your answer should not be refraction. You have to have both of those things satisfied. So let's just look at this again. If this is our boundary, and we have speed 1 equal to speed 2, when that sound comes in, it's going to travel straight forward. It's going to go same path into media 2. So when they are equal, there is no refraction. And that all has to do with our second rule. But we do see that things change when we change up those speeds. So again, we have our boundary. We have speed 1 and we have speed 2. And this time, let's say that speed 1 is greater than speed 2. So here comes our sound beam at that oblique angle. And what we are always comparing our angles to is what normal would have been if it existed. So it's this angle here is the angle of incidence in speed 1. And whatever the alligator's eating, whichever speed it's eating, that angle is going to be the bigger angle and have the faster speed. So the angle of incidence is going to be bigger than the transmission angle. So in this example then, the sound is going to change a little bit, making that transmission angle smaller than the angle of incidence. And that is because our alligator is eating speed 1. It wants the bigger angle. It's going to eat it. So angle of incidence when speed 1 is greater than speed 2 is going to be bigger than the angle of transmission. Now let's go ahead and flip-flop that around. Again, we have our interface. We have speed 1 and speed 2. This time, let's have our alligator eating speed 2 because speed 2 is now going to be greater than speed 1. So remember, we're always comparing to our normal angle. Here comes our oblique angle of incidence. So here's that angle. The alligator wants to eat the bigger angle. And so what we're going to see is for speed 2, it's going to make a bigger turn. And that transmission angle also is bigger. So angle of incidence is also going to be less than the angle of transmission. So when the angle of incidence is smaller than the angle of transmission, that means that speed 2 is going to be faster than speed 1. And all of this has to do with Snell's law. So we know with Snell's law that the sine of the transmission angle over the sine of the incidence angle is equal to the speed of medium 2 over the speed of medium 1. And so if we wanted just to plug in some arbitrary numbers here, let's say speed of medium 2 is 10 and speed of medium 1 is 2. Knowing that the speed of medium 2 is, remember, the alligator wants to eat the bigger angle, which goes along with the bigger speed, I will expect that the sine of the transmission angle is going to be bigger than the sine of the incidence angle. So again, let's just put an arbitrary value in for the sine because I don't want to confuse you quite yet at this point with some other values. But let's just say the sine of the angle incidence value has a value of 3. To figure out then what the transmission angle is, we actually cross multiply. So now we have 2 times x equals 3 times 10, which is 30. Divide both sides by 2, and we would get 15. So that proves that yes, greater speed for speed 2 means the alligator is going to eat the bigger angle, which is the angle of transmission. We can flip-flop that around. Let's say then that speed 2 now has a value of 5 and medium 1 has a value of 8. And let's say that the sine angle of incidence is going to have a value of 2. All right. So knowing what I know about these, speed in medium 1 is bigger. So if I had to guess, whatever value we get for the transmission angle is going to be less than 2, but we can always double check. So 2 times 5 equals 10, and that's going to be 8 times question mark or x, 10 divided by 8 to solve for x, and we are going to get 1.25 as an answer, and so that indeed does check out. Speed in medium 1 is 8. It's bigger than speed in medium 2. So the alligator wants to eat the bigger angle. And we do see then that it is going to eat the incidence angle, which is bigger than the transmission angle. So hopefully looking at kind of generic numbers being plopped into Snell's law helps us understand a little bit more about why this is happening. But honestly, I think knowing the rules is step number 1. And then remembering that the alligator always wants to eat the bigger angle and the bigger speed. So if speed 1 is greater than speed 2, then angle of incidence will be greater than the angle of transmission. If speed 1 is less than speed 2, then the angle of incidence is going to be less than the angle of transmission. And if they equal one another, then the angles are also equal. All right, question number 5. And question number 5 says, how do we account for scattering and absorption, not just reflection and transmission? So a good question, but again, a question that doesn't have a very straightforward answer, nor an answer that we even really need to consider for ultrasound physics. There, again, is a lot of math that goes into it. And we need to remember that the things that we're talking about, like with reflection and transmission, while we can kind of bring them to like a broader, more tangible scale when we're talking about reflection and transmission, these are actually happening at such a minuscule scale in the body that all these things are kind of happening all at once. Sound is interacting and refracting and interacting with all the tissues in different ways, and there's just so much going on, more than it truly just being you have a transducer, it sent sound in, and it bounced off of something and sent it back. Like, that's not actually what's happening in the body, but this is the basic science behind it. And so to get into that part of it, and like I had said in, I think, a different video, like, I don't consider myself a physics genius by any means. I understand ultrasound physics, what we need to know, and how to apply it. But to get into like those nitty gritty details about physics is not my forte, and it doesn't need to be yours either. And I would encourage you, if you are interested in that kind of stuff, to look up some other resources. There are tons of books out there. There's tons of articles that people have written that are really good at all that stuff and talk about it. It's just so beyond the scope of what a sonographer needs that I haven't studied it, and I wouldn't encourage you to necessarily do it at this moment in time either. That being said, though, when the sound does interact with an interface, like when we're drawing these out, like we have like these large spaces and we're like, this is the interface. You have to remember, like, every tiny little structure in your body is an interface. And so if we're talking like nanometers in between some of these structures, and there's an interface, there's going to be a sound reflecting or transmitting, and then it's going to hit another interface in less than another micrometer. And so these things are just happening so quickly. So much is occurring in the body. So much destructive and constructive is going to happen with the waves. It just gets really, really, really complex. So when we are talking about reflection and transmission, when we get to an interface, it is probably easiest just to talk about it in that sense. But remember, we're just talking about the interface, that one little slice of space in which two media are abutting one another, and what happens at that interface. And whatever gets transmitted into the next one, something will happen in there. Maybe some of it will get absorbed. Maybe some of it will scatter through there as well. But remember, then we have an interface like shortly thereafter it. And the same idea would happen. Like whatever gets to that next interface sound-wise, then that's how we would consider, or what we would take into account when we're trying to figure out like IRC and ITC and that kind of stuff. So in a general sense, we probably are considering it when we just talk about reflection and transmission. We're just not getting into the math of scattering or the math of absorption. And there definitely are formulas depending on the impedance of tissue. Because remember, impedance is density times propagation speed. Density has a lot to do with absorption. And so it can be calculated. It just is beyond the scope of what we need for sonography. And our last question is number 6. How would oblique incidence occur? Oblique incidence is anything other than 90 degrees. So quite often your oblique incidences are going to be your more common incidence angle. So we have our transducer up here. Sound is coming straight in at a 90-degree angle. This is our normal incidence. This is 90 degrees. Anything other than 90 degrees is considered oblique. So if I just angled ever so slightly off to the side with my transducer, now my sound is going to come in at an angle. So a lot of it has to do with how the structures lie in the body, and then you're angling at those structures as well.